All right, so I'm Sawood, research lead of the Wayback Machine at the Internet Archive. And today we'll be talking about decentralized web archiving and replay via InterPlanetary archival record object. That's a mouthful. I've been working on decentralized web archiving for quite some time now. So today we're talking about a little bit like how web archiving works, and then what did we try to make it decentralized, and it kind of partially worked, and then what lessons we learned and what are our next plan to make it the next level. So that's the outline of what we are going to talk about. Those of you who are not familiar what IPFS is, it's Interplanetary File System, and the name itself contains interplanetary, which means you can take it anywhere, interstellar even, right? And the file system should work and resolve, right? So the idea is it's a content addressable file system where the location of the file doesn't matter. The ID of the file is derived from the content itself, like calculating a hash and so on. And then using the protocol in a peer-to-peer network, you can ask like, hey, do you have content that matches this CID? And so in this case, the very same picture of that poor dog coming from foo.com/spacedoc.jpg or example.org/uri.jpg, doesn't matter as long as those bits are exactly the same, they will yield the very same hash. And when you are resolving, you just say IPFS cat or whatever tooling you are using, you give them the hash and you'll perhaps get the content out from somewhere. So there's a web page, rather simple web page. What does it mean to archive it? One might take a screenshot of it and say it's archived. Sure, that sounds like a fair proposition, but it won't be interactive anymore. Some information will be lost, like hyperlinks and all, right? So how about saving the source of the page, right? You save that. That's another form of archiving. But we can do better. If you access that page from curl or something or any other interactive library, you'll see a bunch of HTTP headers shown up on top, right? Those were lost if you were just saving those the page source. So how about preserving all these, because there are some important information in there. And that's where WARC files or WARC records come into picture. You take the HTTP payload, on top of that HTTP headers, and on top of that there's an envelope of WARC record headers. All these things put together make one WARC record. And you can have multiple of these concatenated one after the other. That becomes your WARC file. So again, preaching the choir part here, right? You all generally are familiar how it works. So this is how, roughly speaking, how Wayback Machine works. You have these WARC files, you index them, you make CDX index out of it, and then when someone makes a request to play something back, you try to find the record in the CDX file that will tell you this piece of information is present at this offset in so-and-so WARC file. Go grab that data, unpack it, do some rewriting, and play it back. This is our initial implementation of decentralized web archiving solution called InterPlanetary Wayback. It kind of works similar to how regular Wayback Machine works, except in this case, the indexer component ingests WARC records basically and stores individual WARC data into IPFS network basically. So it doesn't talk to WARC files when it's trying to play back. It just fetches that data from the network. And in the CDX file, instead of saying this WARC file at this byte offset, these many bytes, the information is not stored there. It's just the hash or the CID of that particular piece is stored in the index. Okay. Other workflow is roughly similar. So here is what happens. You create a WARC file. There is the HTTP header payload extraction. So instead of putting the whole thing together in IPFS, we separate it in two parts. The payload is separate, headers are separate. And we do it because it gives us the opportunity of deduplication. So the payload portion is generally static, doesn't change often on certain sites, but the header will always change. There is a date header that changes every second. So if we included the whole thing together, then we won't get like the unique content each time. So that's why we separate it out, and we store those both blocks in IPFS, and we get two pairs of a pair of digests that we store in our CDX data. Like on both the pieces are there. So when we are trying to index it, all these records for these individual WARC records go into CDXJ files with their corresponding header and payload digests. And at the time of lookup, it's the same idea. Someone is looking for a specific URL at a given time. We go and resolve it from the CDXJ files and try to get the two pieces from IPFS, combine them, and reconstruct and play it back. So that's how it used to work. We also put a little bit of package there called reconstructive in the mix. One of the jobs it does is like it prevents live leakage, or zombies we call it. So if something was going to external.example.net/img/logo.png, we'll say, hey, hold on, you're not going there. That traffic will be routed to the archive, and the data will come from there. So that sits in the browser. It's a piece of custom component, basically, that's also there to kind of give you the banner, archival banner floating on. So this is a tool that exists. It was implemented in 2016 in a datathon in 1.5 days, basically. And since then it was improved. It's working, it's fine, but it has limitations. It's like IPFS is permanent but not persistent. That basically means although the same content will always produce the same hash, and the same hash will always resolve to the same content, but there is no guarantee the content will be available. If no one is paying for storage and maintaining it anywhere, it will be gone, right? And they use for this resolution, they use something called distributed hash tables. And there's IPNS, which is Interplanetary Naming System, where a URL resolves to a hash. So that one is history unaware. So if it was like example.com/logo.png, that resolves to the hash 1 at some point, and then changed to hash 2. The system now forgets about hash 1, that at some point in the past it was so and so. And in our solution, although the WARC records, those were distributed and decentralized, what was not decentralized was the index itself. So that is centralized. So that's not truly decentralized, right? And we propose some solutions around that, like what we can do, like bringing in blockchain and IPNS and Memento in together, and maybe work around, but no one cared about implementing that, right? So this comes to our new proposed implementation going forward. So basically, what we do here is like we are proposing a system where the discovery of these archives will be part of the protocol, and we are not changing anything in IPFS and IPNS. The system will work as is. That's the proposed idea. So we create this object, we call it IPARO, and it has a header and payload area and a little bit nonce, right? You remember this cute animal from now on. So the header part will have the identifier, URIs, time, reference, a bunch of other things that we'll have there. And the payload area will have like archival payload. It could be a WARC file, it could be a WARC record, it could be a HAR file, it could be a WAC-Z file, whatever one wants to use. That will kind of for historical preservation, they can use it. Even it can be used for Git or whatever. Now, so this is how it works. Basically, you will have like a single linked list that going backward, linking back, and this will be immutable because the moment you change something, the hash changes, so you cannot really modify things after the fact, right? So if you want to go to the most recent copy of example.com, you go to IPNS, resolve something like web.archive.org/dweb/so-and-so and /example.com. I will go and find the most recent copy. From there, you can discover previous, and so on, right? For another URL, will be another one. So when you add a new capture to it, what you will do is basically you first create this object, and then you identify what is the current most recent copy that you can obviously resolve using IPNS, and then put the reference of that one in the header, okay? And then you create two entries. One will go to a new entry that will have date and time in the URL. That will always resolve directly to this particular newly created object, even if it goes in the middle. And one will be updated. The most recent will point to the most recent copy, right? Fairly standard stuff. The one problem is, if for some reason one of these blocks is gone missing, now there's a dead block. I mean, you cannot go any further from there, right? So all these prior versions will be not discoverable from there on. How many minutes do we have? All right. Okay.
5 minutes.
All right. So, so we can make it a little bit more resilient by not having just the previous capture, but having multiple references to prior versions. Okay, maybe when we are adding something new, we can have the link to the previous version, and maybe the third previous version, 50th previous version, or something like that. So it's kind of like a skip list, I think, right, and jumping all over the place. It comes with multiple benefits. For example, if someone is trying to resolve looking for a specific version, and if they know the date time, they can go directly, and so no lookup required. There'll be an IPNS entry that will point to the exact record, right? But if they are looking for something that is in between something, the exact date time is not recorded, then they can start from the most recent one, or the discovery system can resolve the most recent one, and it can go all the links that it has in the header. It will check the most earliest version that goes close to it, but after that, and kind of jumps several hoops, and very quickly will go wherever you want to go, right? You don't have to go linearly all the way. So, and then the moment you identify the nearest item, you go from there and serve that. So, say one of the requirements in archives is generally to list all the captures you have, like time maps in Memento world, right? And if you have these multiple links randomly distributed all over the place, then you don't have to iterate over everything to get all the list. The first one will give you maybe 2 links, and then you choose one of them, and you get like discover 2 more or 3 more or something. And you each time you resolve one of those links, and you might discover new stuff, right? So when there is a point where you're not learning any new stuff, all the links that you are learning are already something that you've collected. At that time, you may stop. But if you want, you can go linearly as well, because the previous link will always there. So this is the idea of like finding a closest version to a specific time. I think I've already described it in a different slide. It's like you are jumping from, taking longer jumps to go to the closest version that matches the date time or is close to that. I just talked about the building these all the versions, right? Now here's the thing. So then we go about, if we are putting all these headers and body and everything else in the body portion, it will be unique each time, right? So how to store it efficiently and still leverage the deduplication. And that's where there's a feature in IPFS where you can actually tell how to decide how much will go in each block. By default, we'll have like a default block size, and we'll slice those things that way, and we'll create a Merkle tree. But you can say, hey, you know what? I want the first block to be these many bytes, the second block so and so, and so you can strategically slice your object where the pieces, there are certain pieces that won't change, and that will remain as is, and it will be reused, those same CID. And there is a nonce thing, right? At the end, why do you do that? I mean, you can add like 1, 2, 3, 4, 5 or any counter there, and each time try to calculate what will be the hash. And if you're looking for a specific prefix, like in this case, DWeb 2022 or something, you keep changing the nonce until it matches. At the time of playback, it can be removed, but this will allow people to kind of group things together just by looking at the list of the CIDs from a collection. They'll say, oh, all these belong to so and so group. So that's the little trick there. With that, a bunch of acknowledgements to people who help in this whole process. Some reviewed these drafts, some reference to other similar materials and funding and whatnot. So what is next? We have not implemented it. It's just a concept version at this point. We have not implemented or not evaluated these different mechanisms of making resilient chains and whatnot. we need to write a technical report. Actually, there is already a publication around that, but we may want to expand more onto the evaluation and implementation side of that. And at this point, we are welcoming any and all contributions and feedback on this one. So to wrap it up, so we talked about anatomy of web archiving systems, and then we described our earlier attempt of interplanetary wayback and what were the limitations of that. We also talked about this interplanetary archival record object that we introduced. It's a self-contained, mechanism that you can store in IPFS. We also talked about immutable linked list for index-free discovery and resilience. This is what actually allows us to not have a CDX file and float it around as a centralized discovery mechanism. Then we also talked about deduplication by piecewise storage and CID grouping using nonce. With that, I will take any questions.